Welcome back to Boring Astronomy. Last time, we dug deep, figuratively speaking, into the very core of our planet, exploring its unimaginable heat, immense pressure, and the quiet, constant churning of its liquid outer layer that generates the magnetic field vital for life on Earth. We discovered that this hidden, inaccessible heart is the boring, yet profoundly essential engine that drives our planet's geology and protects us from the harshness of space. Tonight, we're going to leap from the familiar core of our Earth to perhaps the most sensationalized, yet fundamentally boring concept in the cosmos, the black hole. Often depicted as terrifying cosmic monsters devouring everything in their path, the reality is far more subtle, more predictable, and, in its extreme physics, even more profound. They are not chaotic destroyers, but rather the ultimate, escapable manifestations of gravity's power, following the mundane laws of the universe with an unsettling, silent efficiency. So, dim the lights, perhaps turn on a fan for that soft hum, and let's ease into tonight's journey together. You've heard the term black hole. It evokes images of infinite voids, cosmic whirlpools, and inescapable doom. But let's strip away the science fiction and focus on the boring, physical reality. At its most fundamental, a black hole is not an object in the traditional sense, like a star or a planet. It is a region of space-time where gravity is so incredibly strong that nothing, absolutely nothing, not even light itself, the fastest thing in the universe, can escape its pull once it crosses a certain boundary. It's the ultimate gravitational trap, a silent, dark prison constructed by the relentless force of gravity. This immense gravitational pull is a direct consequence of a huge amount of mass being concentrated into an incredibly small volume. Think back to our episode on gravity, okay? Black hole is simply gravity taken to its most extreme, yet entirely predictable, conclusion. So, how are these seemingly mysterious cosmic entities formed? The most common type, known as stellar mass black holes, are the predictable end-of-life stages for very massive stars. We briefly touched upon the life cycles of stars when we discussed constellations. After a massive star, one perhaps 20 to 30 times more massive than our Sun, exhausts its nuclear fuel, that boring fusion process that keeps stars shining for billions of years. Its core can no longer support itself against a crushing force of its own gravity. Unlike smaller stars that might gently swell into red giants and then quietly shrink into white dwarfs, or even moderately massive stars that become incredibly dense neutron stars, a truly massive star's core collapses inward with such immense force that no known physical process can stop it. It simply keeps collapsing, crushing itself into an infinitely dense point called a singularity. This isn't a violent, random explosion. It's the inevitable, boring outcome of a specific amount of mass collapsing under its own gravity. The key feature of a black hole's anatomy is the event horizon. This is not a physical surface you could stand on, okay? Instead, it's a theoretical boundary in space-time around the singularity. It's the point of no return. Once anything matter, light, information, crosses this boundary, it's irrevocably committed to falling towards the singularity, unable to escape, no matter how powerful its propulsion or how fast it moves. Imagine a river flowing faster and faster towards a waterfall. The event horizon is the point in the river where the current becomes faster than any boat can paddle upstream. From the perspective of someone outside the black hole, anything approaching the event horizon appears to slow down, get redder, and eventually freeze and fade from view, never quite crossing the threshold. For an object crossing the event horizon, nothing feels particularly dramatic at that moment. It simply continues its journey inward, unaware it has passed the point of no return until it's too late. This bizarre effect on time and light is a direct, albeit mind-bending, consequence of Einstein's theory of general relativity. Since not even light can escape, we can't see black holes directly. They are, by definition, black. So, How do we know they exist? The answer lies in their boring, yet undeniable gravitational influence on their surroundings. We infer their presence through meticulous, painstaking observation of what's around them. For instance, we observe stars orbiting around an unseen, massive object. If a star is whipping around a point in space where there's no visible light, but immense gravitational pull, then a black hole is the most logical and boringly consistent explanation. We also observe accretion disks, vast, swirling disks of gas and dust that are slowly spiraling into a black hole. As this material gets closer to the event horizon, friction and gravitational forces heat it to millions of degrees, causing it to glow intensely, often emitting powerful X-rays and radio waves that we can detect. This isn't the black hole itself glowing, but the screaming, dying gas just before it plunges into the darkness. This feeding process, while appearing chaotic, is often very slow and consistent, another testament to predictable physics. Black holes aren't all the same size. They come in a boringly predictable range of masses. Stellar mass black holes, as we discussed, are the remnants of massive stars. It's typically ranging from a few times the mass of our Sun to a few dozen solar masses. Then there are supermassive black holes, which reside at the centers of most large galaxies, including our own Milky Way, where Sagittarius A* quietly sits. These giants can range from millions to billions of times the mass of our Sun. While their formation isn't fully understood, they act as the stable, gravitational anchors for entire galaxies, influencing the orbits of billions of stars around them. They're not actively eating their galaxies. They're merely massive, boring gravitational wells at the very heart of the cosmic spiral. The profound significance of black holes extends far beyond their monster reputation. They are crucial laboratories for testing the limits of our understanding of physics. They are regions where Einstein's theory of general relativity, our current best description of gravity, is pushed to its breaking point, and where quantum mechanics, the physics of the very small, likely needs to step in. They represent extreme states of matter and energy, offering insights into the very nature of space and time. Their existence proves that gravity, that familiar force that pulls apples to the ground, can manifest in ways that utterly defy our everyday intuition, yet remain perfectly consistent with the universe's underlying laws. They are the ultimate cosmic paradox, objects of immense power, yet governed by predictable, even boring physics. So, the next time you hear the term black hole, remember, it's not a Hollywood monster. It's a silent, unseen testament to the universe's capacity for extreme phenomena, a profound manifestation of consistent physical laws that challenge our understanding of reality itself. It's a region of spacetime created by the predictable collapse of massive stars, where gravity reigns supreme. They are boring in their unwavering adherence to physics, yet utterly captivating in the profound implications of their existence. Next time on Boring Astronomy, we'll tackle perhaps the biggest story of all, often portrayed with great drama, about which we will explore for its quiet, fundamental origins, the Big Bang, how our universe began in silence.